at the National Institute of Standards and Technology in Boulder, Colorado. My research is about creating next-generation clocks that are based on integrated photonics. So integrated photonics are circuits for light where we can create complex functionalities and represents next-generation technology in our research area. One of the key sort of laser technologies that we work with are called frequency combs. And frequency combs, they're the only way that we can measure the frequency of light. By measuring the frequency of light, we can also measure trace atmospheric gases like carbon dioxide and methane. And we can measure the shape of the Earth by measuring the frequency of light. One of the big goals is to transform frequency comb technology from a tabletop apparatus into a technology that we can fabricate like silicon chips, like digital computer chips. But nobody knew how to do that until about 10 years ago. We had a big breakthrough where we were able to figure out how to fabricate a frequency comb on a chip. When we really knew that we were on to something with these chip-based frequency combs, that's when we started to be able to make very accurate, very precise measurements of optical frequency with the technology. Everybody, but especially the postdocs, really understood the implications of what this technology could do. And so a few of the postdocs started a company, Octave Photonics.
Octave Photonics is a research spinout from the National Institute of Standards and Technology. We work with researchers all over the world to enable new capabilities through nonlinear nanophotonic devices. At Octave, we've spent a lot of time to optimize that process and make a really nice, compact, easy to use, and really ruggedized system that can take a photonic chip with advanced capabilities and make it more usable outside of the laboratory.
The collaboration with my group has been really, really successful. This project is a good example of something that's really important to NIST, which is technology transfer. There are big benefits for both directions, the commercialization on the one hand, but also our continued fundamental research, trying to make new discoveries and find even more applications of the device.
One of the key technologies we've been developing in collaboration with NIST is this material called tantalum pentoxide, or tantala, which is a great photonic material because it has a high nonlinearity, which allows you to take light from one color and convert it to light at different colors, and that's where the frequency comb technology can really make use of that to generate very precise wavelengths and colors of light that can be used for very precise measurements in a very compact and portable way.
The most exciting thing to me is that we're exploring research directions that we could never do with the tabletop devices. Nowadays, we're building computers out of the microcombs. We're using them to make millimeter wave signals that could be useful for like next generation cell phone networks. It's those aha moments that almost always lead to like really new cool things to do for years to come.